So here in section 9.5, we will be determining sampling size. So let's suppose that you want a maximum sampling error that's allowed. So that's SE, which is Z alpha over 2 over sigma. And what you can do is plug in the formula for sigma, your standard error of your sampling distribution, and then solve this for n. So if you're looking for the sample size to estimate a difference in population means to within a given sampling error, then solving that formula here, solving that for n, will give you Z alpha over 2 squared, sigma 1 squared plus sigma 2 squared over the sampling error squared. But usually you don't know those population standard deviations, so you use the sample standard deviations. To estimate a difference in population means to within a given margin of error, sampling error, these two sample sizes will be Z alpha over 2 squared, P1 1 minus P1 plus P2 1 minus P2 over the sampling error squared. And again, these are population proportions. We usually don't know those, so we instead use the sample proportions. And then to estimate the sample size for a mean difference to within a given sampling error, the two sample sizes will be Z alpha over squared, sigma of the difference squared over SE squared. And usually, again, we don't know sigma, so we substitute S, the sample standard deviation. So really, this section is just deciding which formula to use and then plugging in. So a little plug and chug here. So let's look at an example. So we want to compare the standardized math competency scores for traditional teaching method and a group teaching method for 6th grade students. Random samples are taken from each population with the following sample data. So we got sample 1, size, X1 and S1. Second sample, N2, X2, and S2. We're given separate means and separate standard deviations. So this is going to be the sample size to estimate the difference in means. And they want us to estimate to within 0.5. So that is going to be our SE. And then we're using alpha is 0.01. So here's the formula from up above. So we want Z alpha over 2, so alpha is 0.01. So we want the Z value that goes with 0.01 divided by 2, 0.005. And that guy's going to get squared. And then S1 squared, so S1 is 2, so 2 squared, plus S2, 2.9 squared. And then divide that whole thing by our sampling error squared, so 0.5 squared. So let's go ahead and find that z-score. So pull up the calculator here. That's the z-value with 0.005 to the right, so 0.995 to the left. So we'll go to second distribution. We want inverse norm 3. Our area is left area 0.995. We're doing z-values, so still 0 and 1 for mean and standard deviation. Use left area, paste it, 576. So this will be 2.576 squared times 2 squared plus 2.9 squared over 0.5 squared, which is 0.25. So let's go ahead and enter that into the calculator. So I'm going to do a horizontal fraction, alpha y equal enter. In my numerator, I've got 2.576. That is squared. And then we've got some parentheses. 2 squared is 4 plus 2.9 squared. Close up our parentheses, divide by 0.25. 329.4 approximately. So this is approximately 329.4. And sample sizes always round up. 329 is not quite enough sample size to get the error under 0.5 like we want here, so we have to round up. So this is approximately 330. So each sample should be size 330, total sample size 660.